For those who are new in this room, my name is Elizabeth Gottmich. I work as a freelancer in Germany, and I'm connected to the Sustainable Sanitation Alliance, where I'm the community moderator for the Designer Discussion Forum. We have 4 presenters and 1 hour, and we actually have 3 females, which is unusual, but we will start with the male. We have Billy Chipeta. I'll tell you about Billy. Billy is Malawian. He's got a BSc in Water Resources Management and Development from Mzuzu University. He's currently an MSc student at Mzuzu University, and also a part-time lecturer of environmental management at the same university. And he's had, for example, 4 years with World Vision Malawi as field development facilitator and wash and health coordinator. So, the floor is yours.
Good morning once again. I am Willie Chipeta, and I'll be here to present my research on technology development for peat sludging, which started in 2014 and shall be completed in 2015. On-site sanitation systems or facilities have been in use in many developing country contexts for excitant disposal on site. And in Malawi, there are about 5.2 million people in both rural and urban areas that are dependent on such facilities. And the management of these facilities is a major challenge, especially in those urban areas where there is rapidly growing informal settlements. And the picture below it is just trying to highlight some of the facilities that are available in the study context of Mzuzu City in Malawi. This just highlights the contextual setting of the research, and the Mzuzu City is located in the northern part of Malawi, and Malawi is in sub-Saharan Africa, for those maybe not familiar with Malawi. And the main issue as a context is that this area has a population of about 133,000 people and a growth rate of about 4.2%. And the formal settlements in this city cover about 48%, and in these informal settlements, 94% rely on on-site sanitation facilities, mainly peat latrines. So it is a very relevant context for this investigation. The major challenges that are being experienced in Mzuzu City is lack of appropriate peat sludging technologies. In Mzuzu City, there are vacuum tankers that are run by the municipal authorities, but also by private authorities. These vacuum tankers mainly patronize the plant areas and empty septic tanks. And the only option that is left for those that are using peat latrines is that they either have to look on the possibility of to dig a new peat latrine and meet its space constraints, but also rely on informal peat emptiers, which are just manual peat emptiers, which can be associated with a lot of health risks for peat emptiers and also the safety staff of themselves. And here is just a picture from one of the informal settlements, Chiputula, just to highlight that this is an aerial pictorial view of a full peat latrine, and which we try to alleviate by possibly suggesting physical technologies that are relevant and contextual to Mzuzu City. Just a bit of background. The main criteria focused upon on the technologies is that we thought of developing a technology that is low cost, effective, safe, and sustainable. And within these parameters, when we did the literature research, we focused upon modification of treadle pump. These are pumps that are normally used for irrigation, and they depend on the suction power to empty, and they use treadles that manipulate a rope which is surrounded by a pulley, and they use piston strokes that move up and down. The upward stroke sucks up the sludge in this case, and also the downward stroke pushes the sludge so that they can move to the discharge pipe. And from this conceptual setting, we now adapted the technologies with the support of other consultants, especially our friends from irrigation, on how we can adapt the technology to do pit emptying issues. So, on the other part is the sketch diagram of the pit pipe, which is the conceptual setting. And on this, what we did is just to replace the rope with a bicycle chain, and also to put pedals instead of the normal treadles that are there, so that we can see if possibly this can also be used as another technology for pit emptying. And discussion on the changes that we have made regarding the pros and cons of the technologies are as follows. Firstly, we believe that the technology can be potentially be low cost and sustainable because all the materials that are being used are found available locally, whether it is the chain parts and the other nuts and bolts are available in many shops in the developing country context. And again, we believe that it can be potentially easy to operate because it can just be almost like using a bike, so that it is literally something that people can easily adopt and use. And also on the safety part, we are looking at the possibility that because the treadle pump, you can just insert a hose in the sanitation hole and possibly just you cycle outside the pit latrine. So that can be also helpful, especially in pit latrines that are light, that sometimes when you try to empty and you are trying to empty it from inside the pit, they can potentially collapse because of the other weakening aspect of the surrounding pit. And finally, we thought that for this technology, the major advantage can be that when pumping with leg muscles, this can be potentially useful and more or less straining than using the upper body strength. And on the con side, we also looked at the possibility that this technology can only perform optimally when the sludge that you are trying to empty is fluidized so that remodeling can take place. And also the part that it requires priming, sometimes by the pit emptiers, this can just be viewed as extra work. And also, we also envision, because we have seen from even other presentations that there are a lot of trash in pit latrines. So there are so many things that can possibly enter the suction hose, so that can cause clogging. So at least this also has to be tackled, possibly as a strainer or maybe a filter, to help reduce the issues. And also, we are looking at the issues of reduced transmission capacity. This is looking at the material itself that we are pumping out. When they are moving through the suction hose, these materials such as the sludge can possibly start in the inside part of the hose, so that we can reduce the actual working flow of the hose and possibly reduce the flow that can pass through that hose. Armed with that conceptual design, and also trying to test out the concept further, we took the concept and started to gather the materials, just showing the fabrication cycle, and we went to some local welders and to show them the design, which actually in the first instance, as we tried it, it did not work, but we had to make some other modifications on site, brainstorming on the feet, and test it on some light mud slurry, and see what is happening, and possibly this can be an opportunity for us that was seen as for reviewing the design for further phases. And so far, we have done phase 1 and phase 2 with the major changes as highlighted in the numbers. As you can see, there is one where we did a cylinder orientation change from 1 and 2, from 1 and 1 in phase 1 and phase 2. But also on 2, we see that in phase 2, we have added a metal rod to hold the crankset, and also the position of the crankset in phase 1 has also changed, because in phase 1, we were only able to do the half cycle motion, which was a bit straining. But in the second phase, we are trying to accommodate a full cycle motion which we believe can be more useful and more easily to operate. And also, the fourth is just the changing of the handle positions. And as you can see, now we just highlight the video on what we did and what was observed. The background voices is just someone trying to share me on. So, from this video, what you can see is that the process of doing the full cycle motion is still in process, and also as we are trying to manipulate it, we feel that even the flow rate was still negligible, because when we tried to cycle, it was able to suck some of the mass slowly, but some of the mud was just settling in the suction hose, and also sometimes there was also a potential backflow because we had not added an unretained valve in the suction hose. So in the next phase, what we are trying to do is to optimize the pump design, looking at the efficiency, the energy requirements, and also the economics parts, so that we can potentially have a design that works. And potentially this can be done by December 2015, which is our deadline. And so when this is done, we plan to do about 5 similar tests on actual sludge based on Radford formula, but also trial it out on 30 petra trains just to see what are the limits and the limits of the performance of the pit pump. Is it a comparable alternative to other existing technologies in Periaba and Zuzu, and therefore looking further at scalability options if it works objectively. Thank you so much.
Okay, thank you very much. I think the video was really helpful to really picture how it could look. Any questions?
Thank you, Willie. This is Jody Gabriele, also from Malawi. I noticed in your equipment you're using 2-inch or 50mm suction and delivery. And I'm thinking, are you planning to use larger diameter suction and delivery hoses? Because in our experience, any equipment we tried with 50mm, the blockage was very frequent. And partly it's because there's large rubbish and small rubbish. But the large rubbish is actually, I wouldn't say easy to fish out, but it's much simpler to fish out, the large rubbish. And it's almost impossible to fish out the smaller rubbish. So when we moved to 75mm suction and delivery, and avoided the 50 or 2-inch, we experienced much easier fishing and far fewer blockages by a very large magnitude.
You are very right, and I think your point is very relevant to this context. And we are already planning on doing some sort of a pipe sizing analysis, or possibly on a larger diameter suction hose, because in also our experiences, whether it has been working with other collaborators such as the North Carolina State University, we have found that there was still a lot of trash in petra trains that can potentially block the suction hose. What we did was just trying to use the suction hose that was available to see how it works in the first instance. Thank you.
Yes, Michael Hoffman from Caltech, Pasadena, California. May I suggest an alternative mechanism for getting the pumping action if you were to adapt a stair stepper mechanism, an exercise device that's available in gyms, where you use your body weight to get the same pumping action that you achieve with the bicycle-like arrangement. I think it would be a lot easier for the person doing the pumping to simply act like they're climbing stairs. You should check the mechanism of the stair stepper.
I believe we can also possibly talk more when maybe we are out of the session so that maybe you can share with me your ideas. It is very welcome, so many ideas that can help possibly put a more effective path than what technologies really we are at now.
Maybe we have time for one more? No? It has to be a short one, please. Okay.
Thank you. I would like to request you to identify like the type of thickness of slides you are going to deliver, and also work on the depth. How deep do you intend to work down into the pit?
Okay, I think those points are also noted. I think given the depth of what the slide we are working with, there are others that are doing big characterization in either it is Polytechnic, but there are also others that are doing in Zuzu. We shall also review that, but also shall review other case studies that are available globally. But we shall also be doing more analysis so that everything is covered as we have rightly put it. Thank you.
Okay, then we better move on to the next presentation. So the next presenter is Shrey Saxena. He did his bachelor's in chemical engineering from IIT Milan, Dubai, and has a master's in environmental engineering from the University of Delaware in the States. He's now studying for his PhD under the guidance of Steve Dentoff, and he's working on a grant by the Bill and Melinda Gates Foundation on breathable membrane and streamliners. And we had a discussion about your research on the discussion forum also done last year, so I'm very curious to see how far you got now with latest developments and updates.
Thank you for that introduction. So good morning. I want to talk about my project on improvement of people sludge dewatering and drying by incorporation of the breathable membrane battery cycles. So I would like to point out a few statistics from the Indian sanitation problem, and I'm doing this because we plan to test these breathable membranes in due time in India. So we have about 638 million people with no access to toilet in India. It's about 59% of the total world population who still does not have, who still practice open defecation, and they still live in India. We have 40% of the urban population in India not having access to improved sanitation facilities, and of course more cell phones than the number of toilets, as it has been pointed out throughout the conference, I would say. So in kind of going through these statistics, I feel that my solution or my thought process on solution to the open defecation in India is basically a matter of space, money, and the attitude change in people. And I hope to address the space and money aspect of it through this project of ours. So in the start, I would like to define these breathable membranes and what they do. So these are pretty much hydrophobic membranes, and the property is that they are permeable to any vapor, like water vapor and air, and it is not permeable to any liquid, like liquid water when dissolved contaminants but present in the fecal sludge. The beauty of this concept is that the pores or the passages in these membranes kind of hold only air and the water vapor. This is a picture of the breathable membrane that we use for our testing. This is a 3-layer membrane, and as you can see, the white membrane in between is the hydrophobic part, and it is sandwiched between a support layer and an outer base fabric. describe our process, I would like to go through the membrane distillation process first. It is extensively used in desalination processes around the world. So we have the membrane between, and we have the hot brine solution on one side and the cold distillate solution on the other. What happens is that due to the partial pressure gradient or the temperature gradient, there is a gradual flow of water vapor from the hot brine to the cold distillate, thereby getting us a concentrated salt solution and a dry solution on one side. So to apply this to our context in management of fecal sludge, you can imagine a 55-gallon drum of this breathable membrane, which would have, say, warmer fecal wastes. You have cold dry air on the other side, and as the process indicates, there would be a gradual flow of water vapor through the breathable membrane, and you would have dry fecal matter on one side and pure water on the other. In terms of field application, we would be applying or we would be testing this membrane system in India, where we plan to do this or where we are starting off our field testing in Kanpur, in two families, in two locations, two slum areas. So it's a simple process. You have a squatting toilet. You pretty much attach a perforated drum containing this membrane liner, and as you would expect, with the cool dry air on the outside, you would get drying of fecal sludge as it gets collected during the treatment. Now to get to the sciencey part of it, I would like to point out that this is what I've been doing for the past 2 years, basically working on trying to describe this process a little better. And now we know that this is the equation that kind of governs this, the flow of water vapor. And it's the stagnant film model that everyone wants to look it up. So as you can expect, it has the two major parts that govern this equation, which is the relative humidity on the outside and the temperature, the average temperature across the membrane. To give you an idea of how these two variables affect it, this is a simple graph which kind of points out that as the relative humidity decreases, you would have increase in the water mass flux, and essentially you would have a higher drying rate when you have a higher temperature or an extremely low temperature. So, we saw how, so we tested this on a small scale process or a small scale system in our labs, and we've done this a few times. So this is a 5-cycle test that we tested one simple membrane with fecal sludge over 5 cycles. And as you can see, the drying rates or the drying characteristics are very similar to each other. So over a period of 5 cycles, we did not see much change or a loss in performance. To express this more, I have these SEM images which kind of point out that you don't have the sludge particles kind of penetrating through the backing fabric or the outer face fabric. It gets stopped at the middle layer, which is actually the process facility. We did some other additional testing which kind of showed us that there is no significant deposition on the fabric when there is complete drying. The top figure can also indicate how it kind of forms a thin wafer-like layer on top of the membrane. So it does not kind of stick on the membrane, but this particular test was a digested sludge test. While with fecal tests, we found out that it was easy enough for the deposits to be washed off rather than forming this layer. A few other characteristics that I would like to point out that we found out. It is in this graph we tested 4 different kinds of sludge or four different kinds of sludge across the membrane, and and we kind of saw that the sludge drying increases as the water content or the water content increases or the solids content increases. So in that order, you have outhouse sludge, weaker sludge, digested sludge, and then your plain clear water. And as you would see in the figure, in the graph, you would have the drying rates faster for DI water every time. We also saw, and I'm sorry for the clarity, but we did some step injection tests, which are more applicable to the field application in India. So we would have a small amount going in and increasing the wetted surface area, which is in contact with the outside air and the sludge as well. It was indicated to us that that increase in the wetted surface area kind of increases the drying rate, which was a good sign. So in conclusion, I would just try to point out that the breathable membranes can dry fecal sludge at the point of collection and storage. Then you have that it should work well in hot and dry climate areas. You have clogging not significant enough to affect the process even after 5 cycles. Hence, it is reusable and cost effective in the long run. And you have the barrel design, which makes sludge disposal and transport easy, safe, and less costly. I would like to acknowledge Bill and Melinda Gates Foundation, my collaborators, Water Aid India, Shravan Bharti, and my lab mates and everyone who's been working on this project for the past few years. Thank you.
Okay, thank you. Well, I'm really curious to see how it really then performs once you take it to the field. Questions from the audience? A little bit faster. But you haven't asked one yet. Please introduce yourself.
My name is Yunus Nissan from USA. I'm wondering, could you tell us more about the cost? The membrane is pretty expensive. We probably need vessels which to understand vibration.
We are still in the process of kind of implementing it in a on a larger scale, so I don't have the exact costs for the toilets with the membrane. Like I pointed out in the presentation, this membrane can be used over and over again. So the initial costs do cancel out in the end because you use it as long as the performance does not significantly hinder the usage in these families. Just to throw out a number, I would say it's about the high performance membrane that we use is about $200 for the whole for kind of fabricating the bag as well as the implementation.
Thanks, Michael. So my question that your graphs show that your final mass is 0. Is it just the mass of water? It must still be some fecal mass left, right?
Correct.
And so does that mean that you're getting rid of all the water in the sludge? And if so, maybe can you speak to what the driver was, or what the chemical activity of water is sludge when you get to the final bits of water?
So I would not say it dries up to 100%. We had control situations when we did these testings, and we still had about so we had about 70 to 80% drying, but it wasn't complete drying. I just don't understand what sort of water characteristics you looking for.
The driest you can get to is when the chemical potential of water in the sludge is the same as the outside.
Good.
Okay, so what level is that? The good data show you get down to zero mass in the sludge. Unless I read them wrong.
I think our scale wasn't sensitive enough, or my graph wasn't pointing out to the difference in the mass of the fuel cell. So we used a small quantity, and I guess that's why the residual mass is not indicated on the graph.
Yeah, Michael Hoffman from Caltech. What about biofilm formation? I would think your membranes are a perfect support system for a biofilm, and especially if it became anaerobic in the system. Have you studied the ability for biofilms to form on the membrane?
Not quite. I would not know much about the biofilm formation on the breathable membranes, but I guess we can talk later and probably figure out if it can be possible.
Okay, thank you. If you have more questions for Shrey, don't be afraid to get on the Susanna discussion forum. Put in the search field breathable membrane and you'll find the discussion and you can ask more questions. So the next presenter is Katja Wolle. She's a research assistant and technician at Wageningen University in research in the Netherlands at the Sub-Department of Environmental Technology. And the current research that she's going to present to us was performed as part of a Bill and Melinda Gates Foundation grant via the London School of Hygiene and Tropical Medicine.
Hello, I'm Katja Wolle, as you already said, and you can see the title of my presentation. As you can see, it has been done in the lab. I saw the other days pictures of pit latrines. I'm happy I stayed in the lab. It's about solids solubilization of fecal matter and black water by means of additives and pit latrine chemical physical aspects. This has already been said, I'll skip it. The aim was to extend the lifetime of a pit latrine. You can do that, of course, by loading less, but if that is not an option, you have to do something else. The substrate that should go into a pit latrine is, of course, human excrement. And if you look at the composition, on average, it's at least 86% water. 86%. So even if you would convert all the organics, you would be still left with a lot of mass. So pit fill is a mass balance water issue and not a COD issue. Of course, COD conversion or stabilization of your sludge is desired. You could define desired pit working as stabilization of the organic matter, of course pathogen removal, but also degradation of the solids, and you have to move liquid in order to extend the pit lifetime. So point 3 and 4 are the key factors in extending pit lifetime. So I had a look at bioadditives. I made a list here. It is 47 of them. I used 2 soils, one from the Netherlands, from the roadside, one from Tanzania, also from the roadside, because soils are sometimes used as a coverage in fecal matter. Also 3 anorganic conditioners, perlite, talcum and diatom earth. 4 commercial pit latrine products, enzymes, 6 of them pure. I made also a mix of that. A fungus culture, 15 pure culture bacteria mixes. They were live or spores or on bran. They were aerobes, facultatives or anaerobes. and I use dung extracts. My thinking behind this was that we are omnivores and the solids we excrete are mainly plant material. Maybe active herbivores do have gut flora that is more suitable in breaking down plant material. So I went to the local zoo and got myself a load of dung from camels, zebras, giraffes, and made extracts from that to see if that might work as an additive. Unfortunately, I was not allowed to travel to Australia and Asia, and so I had to use animals from the zoo. The experimental setup was lovely compared to a real pigletry. It's all in a lab, all controlled, nice temperature, mixing. I used black water as a substrate. That is the content of a toilet with a 1 liter flush and then passed through a macerating pump. To facilitate sampling, I put it through a kitchen sieve to get the big particles of toilet paper out. I tested gas conditions aerobically or anaerobically in a more pigletry scenario of 1 to 1.5 day aerobic and then anaerobic gas phase. And then I compared the substrate with the additive with just the substrate, because the substrate by itself has quite a biological activity and can solubilize solids by itself. So I want to see from the additive the net yield in solubilization. There's no point in putting 1 kilo of additive in there if you only get 500 grams of extra solubilization. This is the result. It's really very sad of the net solubilization by additives. It's all less than zero. In fact, some of the additives have adverse effects on solubilization of solids. It's all less than zero. I must say that the intermediate products, like VFA, at no point hampered the hydrolyzers of these solids. I must also point out that I only looked at the hydrolyzers. Maybe these additives might have other beneficial effects that I did not research. So, can bioadditives help maybe with reducing the pixel height? I've never seen a real pigletry in my life, but I created the simulation one. You see already a little plastic bottle. I used 3 types of mixed pure culture bacteria to create 3 mixes that I used as additive in these pigletries. I used one commercial product, and I used air as an additive and compared them to 2 blank pigletries, which had nothing done to them. This is in fact the setup. It's a 2 liter PET bottle. The top of the bottle is now the bottom of the pigletry, which I covered with a panty-sock fabric and a band to keep the fecal matter in the bottle. And the bottom of the bottle was cut off. That's now the top of the pigletry. To trigger drainage, I put at the bottom of the pigletry some tissue paper to trigger the water out. Now, we have to load these, of course, with substrate. I had several volunteers to donate the substrate to make sure that the substrate was equal in all the pigletries. I used this scientific setup. I collected everything in a mixer bowl, put it in an anaerobic tent, and made all the donations nicely blended with the kitchen mixer. And then scooped them into the pigletries. I did 4 donations into the pigletries over 129 days, and I did 3 donations of the bioadditives suspended in a lukewarm water, like you would do in real pigletry. These are the results. You might notice that I skipped the bacterial mixes because they didn't do anything. The blanks have an average height of the pigletry filled 19 centimeters. The commercial product did little to reduce that, but aeration did. This is mainly by evaporation, I must say. It was not the intention, but I also did the COD and I compared that with a lot of the substrate that I stored in the refrigerator and which I considered the non-treated sample. You see that the blanks by themselves is capable of reducing the COD, but the commercial product reduced it a little bit more. But again, aeration did most. I further noticed that these suspended bioadditives had a tendency to run off as you pour them on the fecal matter. They run to the side of the bacteria. Also was noticed that I had crust formation on my substrate, and I tested this even how strong and how fast these crusts were formed with a texture analyzer from the food department. They were not too happy about that, but okay. And I noticed that within 3 to 5 hours I had quite a significant crust, and this crust persisted even when I covered it over for 15 minutes with water. It only softened with half. Or 5 hours with new fecal matter, it only lost 10% of its strength. So you get stratification in your pit latrines. Crust persists. So the only additive that really worked was aeration here in the pit latrines. I also looked at physical-chemical aspects. Here they are listed: pH, gas phase, moisture content, and temperature effect. The test setup was also again in bottles, all nice controlled, and so on and so on. I used as a substrate black water, and for the moisture I had to use, of course, fecal matter. Now I can tell you, to get fecal matter into a bottle with an opening of 1 centimeter, you use a pipette bag that you normally use for cake decoration. But then you have to ask your substrate donors not to eat peanuts or corn or chew very well. This is the result of solid solubilization or hydrolysis by difference in gas phase. It's quite significant. Aerobic was fast and more complete compared to an anaerobic condition. Initial pH, and look at the end pHs, also quite significant. Moisture and temperature did little. My conclusion is in fact that additives do little or nothing for solid solubilization. They do little or nothing for pit height reduction. May do a little in COD reduction. But this was in lab conditions, quite optimal. Physical-chemical aspects, pH and aeration do have an effect on solid solubilization. Air has an effect on pit film height. And air certainly has an effect on COD reduction. Now I have to speculate. I've never seen a real pit latrine in my life. And if we speculate, what might we expect from a bioadditive regarding solid solubilization or pit film height reduction? I see problems. I see a lot of problems. Additive addition is in fact adding extra fill. It's not much, but it is extra fill. And the contact time is needed between these bioadditives and the substrate, and this is hampered for the reasons listed here. And also the temperatures, they fluctuate. With physical-chemical aspects, you might have more success. But this, I never investigated. What are the options here? Are dangers here? Elevating the pH and aeration, of course, then ammonia might be stripped instead of being nitrified. But if it doesn't nitrify, it will nitrify inside the pit and not in the soil. It will not go to the groundwater. Then, when it's covered over with new fecal matter, it will denitrify inside the pit. And that might be an advantage. This is one of my dumb donors. Thank you you very much for your attention and questions.
Thanks for that, Katja. I imagine that it must have been pretty frustrating research to test all these additives and never any effect, basically. But someone had to do it. I think it's important research.
I'd like to comment on that immediately. It's nice to know that you should not spend money on something, especially when you're poor.
That's what I'd say. So I think that sort of research is very important, even if it's frustrating. And in South Africa, they've also done it on real pits with also 20 or 30 additives, and they also said, no effect, don't bother buying that stuff.
Yes, the group in South Africa, I really have to thank them from the bottom of my heart for the guidelines of doing this testing, and I can confirm all their results. Now, under optimal circumstances, so in real life, it bodes no good.
So, is anyone in the audience who wants to challenge any of this research or confirm it? Or, yeah, over there. Cara Nelson from Berkeley.
I just wanted to comment on the one positive result we had, which was that adding air seemed to make the solubilization increase, but I suspect that that's just a kinetic issue, that anaerobic digestion is probably capable of solubilizing.
I waited for ultimate solubilization, so these tests were anaerobically in 20 days. I got no further solubilization. With the anaerobic tests, I waited sometimes over 120 days until there was no further solubilization. So these are ultimate results.
Well, that is interesting. I don't think aerating temperatures is very practical, but
I was thinking, if you would want to apply something to a real petri tree to extend the aerobic period at the top of the tree, just a little bit. That can be by barrel or a bicycle pump, but you could also think of a conical-shaped petri tree, which makes, of course, the open air access larger and longer. It's just the top layer. You see that compared to fresh matter, and the top layer of the petri tree and the CUT removal is like 50%. And that's just a drop zone. After that, the easy stuff is gone and it slows down. And it drops anaerobic.
Okay, another question or comment? Do we have any suppliers of pit additives in this room who want to visit with? Or effective microorganisms is also often part of this discussion. No. Okay, then I think we move on to the next presentation. Again, Katja. The final presenter in this session is Yulin Cheng. She's a professor at the University of Toronto in Canada. She's a chemical engineer by background, educated in the States, and director of the Center for Global Engineering. And she's also a grantee on the Reinvented College Challenge program of the Bill and Melinda Gates Foundation.
So I think I'm standing between you and lunch. It's a relatively, hopefully not too long a talk. It's a very long title. You don't have to read it. Do this? Chemicals, so we saw this slide on Monday. Alma Boyce presented this as a closed city study done by the Water and Sanitation Program. And showed that there were a lot of issues with the sanitary service chain in many cities. And what we're trying to do, our team and several others, has been funded by our DTC, is to essentially by processing the waste right on site. So we cut out the requirement for a service chain. And so what I'm going to talk to you about at a very high level is what our approach is and the thinking about in our approach so that we get to an off-grid solution and what would make an off-grid solution feasible. So this is an overview of our process. So mixed waste comes in. We have a passive diversion process that separates that dewaters the solid. I see passive diversion and sand filtration. This is what we showed in the Delhi toilet paper back in March. The liquid that goes into the heat pasteurization tank. The dewatered solid is flash dried and then convective dried. Sorry, the formatting got changed. Change computers. And so the solid gets dewatered in one step in diversion and filtration. Then it gets dried. And then the dry solid gets smoldered. Essentially, we're drying the solid and we're burning. It sounds really, really simple. That's it. We just dry and burn. And what we get out of the smoldering process is essentially the inorganics of the feces. The feces is completely destroyed. The temperatures in the smoldering reactor gets up to 600 Celsius. So pathogens are gone. The solid waste is gone. And the liquid is pasteurized. And spends close to, in the phase 2 process, it spends close to 24 hours in a 70 degrees Celsius kill tank. So let me just talk about the smoldering a little bit more. So the saying there that the smoldering has feces and sand mixture in there. Okay, so smoldering is, for those of you who haven't heard me talk about this before, is the actual chemical reaction is the same as a fuel reacting with oxygen to form CO2 and water if it goes to completion. But instead of an open flame reaction where the fuel has been volatilized and the reaction with oxygen takes place in the gas phase, a smoldering reaction is that reaction takes place at the surface of the solid fuel. So oxygen has to get to the surface of the solid fuel and then reacts on the surface. So the difference between that and an open flame is that it's a more controllable process. It's a slower process, but you have to provide porosity so that oxygen can get to the surface of the fuel. And feces is the soft material, it's compressible, so if you have a pile of that, then you're not going to get air to the surface of the fuel very well. So we mix the fuel with sand, and the structure of the sand provides the porosity so that oxygen can get to the surface of the fecal mass. So that's why we have feces and sand mixture. Working with sand is a pain in the neck, but we take advantage of this particular feature as well, which I'll talk about in a little while. And the way this works, this is an infrared picture of a batch column of a smoldering process. So the smoldering front, so we ignite the fuel and sand mixture at the bottom, and then as smoldering takes place, it actually takes place in a very controlled fashion, and that smoldering front, indicated by the red color, would move up over time. And so as time proceeds, we finish burning the entire bed of fuel in that column. And so that's basically how smoldering works. I draw the circle here. There are a lot of different steps here, but I'll point out that what we did in phase 2, what we showed in the Delhi toilet fair, the flash drying, the convective drying, and the smoldering all takes place in the same vessel. So it's a single chamber. So that's the overall process. The slide showed the mass flows. And what I want you to focus on in this slide are the red arrows. And the red arrows have to do with what we do with the energy flow within this process. As I said, with smoldering, we make use of sand. And even though sand introduces a complication in terms of material handling, we take the advantage of the fact that the sand can act as a thermal battery. So when we generate the heat by burning the fuel, the heat that's generated actually is retained in the heat. A large fraction of the heat that's generated can be stored in the sand that's being used. So we think of that sand as a thermal battery. So at the end of the batch process, we apply sand making. And that hot sand will introduce the next day's batch of feces into the reactor, mix it up, and that hot sand actually flash dries the feces very quickly. It's a very, very rapid process. It happens in a few minutes. So the advantage of that is, in addition to being able to dry very quickly, is that we generate, this is a fast process, we're actually generating steam very, very quickly. The steam is generated in just a few minutes. So we can then direct that steam into the heat pasteurization tank, and through condensing coils, condense that steam and use that enthalpy of condensation to heat up the contents of the liquid tank. And one more time, at the end of the one-day cycle, the liquid in the pasteurization tank is still somewhat warm. We run it through a counter-current heat exchanger to preheat the liquid going into the building. So the energy management aspect of what we're doing, we store the heat generated using the hot sand as a thermal battery, and we use that once to flash dry the feces, use it a second time to heat up the liquid, to pasteurize it, and use it a third time to preheat the liquid going into the tank. So this is what we showed in Delhi, and those of you who saw it, it was a beautiful thing, and it was a little big, and I'll admit that. And but it was a snapshot in time in terms of our design iterations. But what we're very proud of was that it was actually a fully integrated system, and we had run it multiple times, multiple days, either single-day cycles or multiple-day cycles, and run it very successfully. There are a few things that we didn't like on those 2 days, but also, and obviously, kind of, would be, at this size, it would be kind of expensive. But we also didn't like the amount of energy that we used, 4 megajoules per day. And we did a very careful analysis of where all the energy costs came from. And the 2 biggest energy cost items was the daily ignition. So to ignite, to get the smoldering process going, you have to ignite the fuel at the bottom. It took 1.6 megajoules for that every day. And the second was 1.4 megajoules for convective drying. So what happened was that even though this flash drying worked really well, we didn't get it to the point, we didn't get the feces dry enough to the point where it would smolder. So we then would pump air through this mixture in order to finish drying to the point we could. And this was actually turned out to be, in hindsight, that was a really stupid thing to do. And it's very inefficient and cost a lot of energy. I won't go into all the reasons why, but that's why. So the lessons we learned from all that at the end of phase 2 was, and there are many things, but I'll just highlight the things in red. We like the fact that we use sand as a thermal battery, and as I said, we were able to make use of heat generated in a very efficient way. We like the process of flash drying because it was so fast. The things we didn't like the energy that we had to spend to ignite the fuel every day, and we didn't like convective drying. Now, not just because of the energy cost, but also if we're bringing air from the ambient in order to dry the fuel, then that process will be very dependent on the ambient conditions. So under high relative humidity conditions, that process will become even slower. And so we want to remove convective drying in the next step of our process. So just to say a little bit more about the drying and dewatering aspect of things. So healthy feces is about 3 to 1 water, 75% moisture content. Our smoldering target, if we can get it down to 1 to 1, then we could burn it very robustly. We could do it at 60% as well, which is about 1.5 to 1. But 1 to 1 is a robust number. The input we had, the mixed waste of solid and liquid that we had going into the process, was about 50 to 1. And of that, 3 to 1 was water and feces. So 47 to 1 was the free water. The process that we showed in Delhi we're able to de-water. By the time we de-water, the amount of water to fuel ratio was 4:1, which meant we had about 1:1 free water remaining after de-watering. Okay. If you compare 47:1 down to 1:1, this is what we're looking at before. That's pretty good. We got rid of about 98% of the free water. Okay. So if you compare these two numbers, that's great. But the energy we had in the hot stand wasn't enough to flash dry this 4:1 down to 1:1. Okay. But if we were able to remove all of that free water, then the water solids would have about 3:1, and then our drying requirement to get down to 1:1 would just be 2:1. And at that level, we would have enough energy in the hot sand to flash dry and not deal with not have to convective dry. So since the Delhi toilet fair, and I can't share a lot of the detail, all the details with you yet. So just at a very high level, we have been able to develop a continuous molding process. This is one of our big goals. Because that would then reduce the ignition energy. We wouldn't have to ignite every day, and it would also reduce the size and cost. So we've been able to do this. We're very happy with this particular progress. And the reactor that we're using now is only a 6 centimeter diameter reactor. And we've been able to show if you're going to run this process continuously for a 10-person scale, you're only smoldering, you're only processing about 30 grams per hour. And imagine trying to keep a continuous burn at that slow of a rate. We've been able to achieve about half of that. And we've also been able to do water down to about 75% moisture content. So we've been able to do this for healthy feces. We're trying to work on what to do with diarrhea. And some changes happen once we move to a continuous process. So there's some tweaking we have to do with the energy manual. That's in progress. So we're building subsystems and prototypes. This is the first version of the reactor that we showed that we built. This is altogether. This is one meter. This is 6 centimeters, and the active part of this is only about 30 centimeters. And our plan is to build a fully integrated prototype by March. First version and second version in July, and with varying degrees of functionality testing. So if all this works, the final system, our estimate of the electricity requirement is only about 0.15 kilowatt hours per day. And the key here to make this work out, just to tie it back to the initial point, the key is in managing the energy efficiently so that the amount of extra energy needed through solar panel or so forth is minimal. And so that's the final point I'll make on that. And that's it. That wasn't on the slide except for that slide.
Thank you for that presentation. Do we have any questions? Louder than before.
I was wondering, how do you separate hot sand from the cold and inert sludge?
How do you separate hot sand from sludge?
Because you're returning this, aren't you?
Okay, so as the smoldering front moves up, the material above the sand, above the front, is a mixture of sand and feces. The material below the front is just clean sand. All the feces has been burned off. So we make use of what's underneath.
Do we have anyone else who wants to ask a question about this process? Complicated, taking more lunch to think it all through. But once again, we would use this, you can discuss it on the discussion forum. We had some posts on the website. And
I wanted to also point out, if you haven't heard in other sessions, that we've got these cameras here, and so all the presentations are being filmed, and the plan is to make them available on the YouTube channel of the Sustainable Sanitation Alliance, so that if you've missed interesting lectures from the other rooms, you can view them. You can also then share them with your colleagues, and I hope it's going to work out as we planned. I think it would be very exciting to have all the presentations available for anyone who has internet access. If anyone has any concerns about their presentation being online, then please speak to the organizers. Of course, we're not going to force anyone. If you have some secrets that you don't want the world to know, then that presentation will not be online at your request. So the session that we had 4 presentations, and I was trying to come up with a common theme, but I think there was not so much a common theme, but they were all interesting. Willie from Malawi told us about a new technology for pit emptying that is using the power of the legs. And then we had Shrey talking about breathable membranes. How can these membranes be used for in situ drying of fecal sludge in pit latrines? And he's going to test it soon in India to see if it really works. Katja investigated bioadditives in pit latrines. She confirmed that there was no effect, and I found it interesting, this simulation of a pit latrine by using that PET bottle. I've never seen that before. I don't know if it's a good model of a pit latrine, but there you go. Somebody tried something new there. And then Yuling was explaining to us her process, which is an on-site process for treatment of human waste on site. If it works out, then we can do away with these ship flow diagrams altogether, which would be awesome. I don't really like them anyway, ship flow. Yeah, I don't like that term. Yeah, and she was telling us about the sand, how she uses that as a thermal battery, which I thought was also interesting. So thanks very much for your attendance, and enjoy your lunch.